this Mandelbrot set app that I've been working on, I have this user interface where you're able to like zoom in and pan like in Google Earth, but
Mhm.
this is not fast enough for me. I want this to be faster. It's okay. Like you can see it takes a while to get a high resolution image here.
Uh-huh.
If there's a way to make this better, then I wanna make this faster, more
Mhm.
responsive. Um, and I know a thing that can do it, and that's the GPU Graphics Accelerator that's on most computers nowadays. Have you
Okay.
heard about the GPU? You're not a gamer, but gamers would know what this is. I'm not a gamer either, so I only have cursory knowledge of the GPU. But oh, actually, on your computer, it's basically a separate CPU in your computer, other than your main CPU, and it's it's a CPU that's designed for graphics, designed to speed up your graphics, and
Mhm.
it doesn't have only one CPU. It's actually got tons of little CPUs on it.
Mhm.
So it's like I remember when I was in college, one of my professors would say the CPU is like a hungry horse, and you want to feed it as much as it can eat to to keep the throughput of the computer going.
Mhm.
A GPU is like you got a herd of horses
Mhm.
there waiting to do work,
Mhm.
and it's targeted for doing computations that get rendered directly on the screen. Although it can be repurposed to do other things as well. About this Mac thing, and you can see that on my Mac, my graphics processor, my GPU is the Intel Iris Graphics 6100 chip. Um, so um, and I've never learned that much about my GPU chip, but I did a Google search the other day,
Mhm.
and I looked up some specs on it. So this is the graphics chip that's inside my computer,
Mhm.
and the GPU name is actually Broadwell GT3. But this is a pretty crappy graphics chip because the gamers like because this is my Mac is I have like a 5-year-old MacBook Pro.
Uh-huh.
Um, People who are into gaming, they would buy a NVIDIA graphics chip, a GPU from like if you Google for best GPU, um,
Oh, that's expensive.
wow, $10,000 for a graphics card. So yeah. So gamers would what's the best one? There's the Radeon. It's got two fans because it's gonna get so hot. You know, all of these they have they have like some of these have 1,000 CPUs on the graphics chip, like 1,000 tiny processors on the graphics chip, and that's pretty insane considering that your main CPU maybe has dual core or quad core, has 2 or 4 CPUs on your main chip.
Uh-huh.
The graphics card has 1,000 chips. I looked up the spec of mine, and it seems to say that mine has 384.
Uh-huh.
They're called shaders. Um, and a shader is a CPU that's dedicated to doing computation to calculate the color of a particular pixel on your screen. And
Mm.
the reason we need this is because if you want the smooth scrolling that you see is pretty smooth, or on an iPhone. That was one of the major selling points of the iPhone. That like the very first iPhone that came out, it has smooth scrolling, right? like it was very responsive. The graphics was very fast, and the reason they were able to do that is because they had a GPU that can calculate the image that needs to go on your screen at any moment using extra processors. Like the CPU has got extra help basically to calculate the image that needs to go on the screen.
So how do you make this work? Or do you have to, like, how do you interact with their API, or do you need to in order to calculate faster?
Yes. In order to write programs that run on the GPU, typically, this is not the only way, but this is the typical way. You use, first of all, you use a framework called OpenGL. So OpenGL has been around for many, many years. Like I play with it in college, in computer graphics class. It has evolved and changed a lot since that time. And nowadays in modern OpenGL, one very big part of OpenGL is shaders, which is these shaders on your GPU, and there's a shader language called GLSL that you would code in to write programs that would run on your GPU. And this is usually the domain of game developers. However, anyone interested in computer graphics might get into this, but this is GLSL code. It looks mostly like C, so it shouldn't be that foreign, and it wasn't too hard to pick up for me. It has these types these vector types and matrix types that are built in, and the page I'm looking at right now is actually documentation for WebGL, which is OpenGL for the web, which is possible as well, and that's what I want to use for my thing.
Question. So how can that GLSL shaders like integrate with the web?
So the short answer, I'll go to the short answer first. The short answer is the canvas. I'll go to the can I use page to show you the browser support for WebGL. Okay, so basically all the major browsers, even IE, has support for WebGL. And the way you use WebGL is part of the Canvas API. Normally, when you use the Canvas API, you're like canvas.getContext2D, and then you get a context, right? And then you can draw your stuff.
Yeah.
But now instead of doing that, you say get context WebGL, and you get a handle that's GL, and the GL API is completely different from your normal 2D context. And the way you interact with this GL, there's a bit of a learning curve, I have to say, but it's very similar to OpenGL, and if you have learned OpenGL, this will be very familiar to you. But if you haven't, then you have to go through that learning curve. I think I want to draw some diagrams to give you a big picture of how things work. First of all, I have to admit I'm very much a beginner at this stuff, so I don't claim to be authoritative on this. But the way I understand it is you have a GPU, but on the inside there is hundreds or even 1,000 tiny CPUs in here.
Okay.
There's a lot of workers. We want to get these workers to work, basically. We want to give them jobs to. So one of the problem of generating this Mandelbrot set is you saw what we were, like even in the little demo that we did, it was very slow, right?
Yeah.
And basically we had to go through every pixel on the screen and do this loop. And you can choose how many iterations you want to go. But if you want to get, higher iteration to get more detail, it's going to take longer, right? And here I chose to go 1,000 iterations with the sort of high resolution image I'm generating. It's a lot of work. So what we're able to do with a GPU is those work because the calculation for every single pixel is completely independent of the calculation for a different pixel. So they're completely independent work. We can do all of them in parallel if we wanted to. And so the trick is like, hey, I'm gonna package up this program. I'm gonna have this draw. I'll call this program draw Mando pixel. I'll package a program just to draw one pixel on a screen, and then it's gonna have inputs and it's gonna have outputs, and the inputs will probably be for which pixel on the screen am I drawing this for, right? And the outputs would just be a color. Like the inputs would be like the location, probably just the location, probably, and maybe some other stuff that like the number of iterations, maybe, or the color, what color palette if you want to change color palettes. But whatever input you want to give to it, you can define them and then pass them in. Number of iterations. And then you write this program, and it's gonna be written in GLSL, or also called the shader language. I guess SL means shader language. So you write this program and you create a job running this program for every pixel that you want it to render on the screen. And we just dispatch this program to every available tiny CPU that's in your GPU and have them work on it all at the same time.
Question, before, if you don't do this, what is the current way of work, the GPU working? I guess the same thing needs to be done. So are they done like one by one? That's why it's slower?
Oh, the implementation that we did, it does not use the GPU at all.
Okay. So in this case, the GPU wouldn't be used at all, or
right.
Okay.
Correct.
So the GPU only comes to work when you write specific program to make it work. It does not tap into the operating system. Okay.
Exactly. So last time we did this, right? We have a nested for loop, and then each pixel we have to call this function, and then it's doing this for loop here. All of this stuff is running on your CPU. And it's in JavaScript is single threaded, which means it's only using one of your CPUs. Even if you had dual core or quad core, it's still only using one of those, 2 or 4. And all of the work is happening on that CPU. If you're able to employ the GPU, you're like calling in the cavalry. It's like it's like one of those I don't know, the gangster versus police movies. It is the one, like the police infiltrates the gang, and then like the cavalry is coming, and then all these police cars come rushing in. Like we have hundreds or thousands of workers that will work on your job in parallel. So instead of you going through here, when you're doing a for loop, you're doing one after another. but we're saying no, do all of the, for every XY, make that a job and send it out send it out to these tiny processors and have them come back with the color, and then all the color will go into this buffer that becomes an image buffer, and when it's all done, it gets splatted onto the screen right away.
Oh, okay. So this can only do like rendering related stuff. You wouldn't.
No, you can repurpose it to do other things, such as mine Bitcoins, or any or any computationally expensive thing, because you could have it compute the graphics buffer, and then you have other code read the data back out from the buffer to do other stuff if you want to. So you can repurpose it to do other computing intensive things, but it was designed for the graphics case though. So I guess this is a very simplified picture of this, but to get more detail, there's actually this. First of all, this program that you're writing is called a shader, right? We're writing a shader. And if you Google for shader, there's plenty of info on the internet about shaders. There are two types of shaders. The one is the Vertex Shader, and the second one is the Fragment Shader. And the Fragment Shader is the one we would use, because the Fragment Shader is the one that will work on every single pixel that we're rendering. The Vertex Shader is used for marking regions that are to be painted by the so the Fragment Shader is like the bucket fill tool in your image program. It's like, hey, draw a region for me, and then if you have a region for me and tell my Fragment Shader to paint it, I'll go through each pixel and use this program to color each pixel within the region. Okay. The job of the Vertex Shader is to define what these regions are. So the job of the Vertex Shader is like, because usually in your program you have a representation of objects in the world and the locations and size of each object, and usually that's different. Like if you have a box, then you probably represent that as hit this point and 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 this point, etc. In your program, you have those data structures representing those points. And a vertex is saying, hey, I don't care what your 3D world is. I just want you to tell me the visual representation of your box. And usually you describe it as a series of triangles, because in computer graphics, we have invented fast algorithms for dealing with triangle. So if you have a box like that, you would separate it out into these triangles.
What?
Yeah, I know, it's kind of crazy. You just represent your box as triangles, and a vertex is a vertex of a triangle usually. So you send for each point in a triangle, you would package that as data, like the coordinate of this is x, y, x1, y1. The coordinate of this is x2, y2, etc. You would package these coordinates as like, this is vertex 1, this is vertex 2, this is vertex 3, this is vertex 4, etc. So for each of these vertexes, you send it into a Vertex Shader program. And then the Vertex Shader program can do a translation for you if it's needed, because you depending on which perspective you're looking at this object, from, you might need to translate the location of the object onto a corresponding pixel on the screen. So you're like, this should map to here, this should map to here, this should map to here, and that's my first triangle. So the job of the vertex shader is to translate the coordinate in your 3D world to the coordinate system on the screen.
Okay.
And then once the vertex shader has decided what that region is based on these vertices are on the screen, and then it sends it over to the fragment shader and go through each pixel within the region and decide a color for that pixel.
Okay, so basically the idea is you tell them the X and Y of, well, I guess the X and Y that you tell them in the context, in the canvas context, would that be the canvas coordinate X and Y? Or what, like, how do you define the X and Y in that case?
In OpenGL, the X and Y is usually scaled so that the viewable portion on the screen has a 0, 0 in the center. You can always scale it to your liking, but but there's a standard viewable port that so the X and Y is based on that standard viewable part.
Okay.
And then
so
you have to take care of scaling it to and from the screen coordinates. But when you're sending the X and Y coordinates to the vertex shader, it's based on the coordinates in this world.
Okay, I see.
That's the high level concept. I'll just briefly show you some code. We don't have to go too deep into it. It's a bit much for someone who's new to it. I really felt like I was like in a foreign country for a week coding this thing because it's so different from what I normally do. So here's my canvas, and this is nothing different from what you've seen before. But the part that is different is, first of all, you when you get context, you get a WebGL context, and then you have this GL object to work with. Okay, this is the setup code. I create a vertex shader, and I compile it. And here is where I give the source code to the vertex shader. And the source code, why did I even make, I used someone else's code. So this vertex shader code, I have it as an import from here. So this is my GLSL code. And in my case, the vertex shader is extremely simple. All I had to do was define a rectangle that covers the entire screen, and then get the fragment shader just to paint every single pixel, right? So this is basically saying, and each vertex is gonna get sent into this program, and that vertex is gonna be this position here. And I'm just saying, just take the position as is. I'm not gonna do anything different to it. Back here. So I compile the vertex shader, and if there's a problem, I'll print an error message. That's important because otherwise it was hard to figure out what went wrong. And then I do the same thing with the fragment shader. The fragment shader source. I'm using this one. I'll show you the simple one. So I could change it to the single. There's another story too, which we don't have time to go into. This is the program that paints one pixel of the Mandelbrot set, and the coordinate is given by this GL point coord. This GL point coord is the location of the pixel that I'm painting. And then I have the transform matrix to scale it, because that's for the user to pan and zoom. So the matrix has information about how much to scale down into, and how much left and up down offset to apply to that point before going into it. And then this is the iteration. I'm iterating 1,000 times, and then I'm doing that calculation in terms of their vector. And then at the end, I'm doing a coloring scheme. I think I might show you this. So this is, yeah, more or less what I had before, but you can see I'm zooming in. It's not perfectly smooth, but it's pretty responsive and definitely much faster than my version. Like with still high quality of detail, even as it's zooming in. But the problem is now we're starting getting pixelated. And that's the other story. Maybe I'll save that for another time.
Okay.
Because that's a long story in of itself. So yeah, you have to do this stuff, compiling the two shaders. You do that programmatically, and then you plug it into the program. You create the program, attach the shaders to the program, and say link the program. That's like compilation, compiling the program. And then you tell GL to use this program. And then the way you actually draw to it, you say draw erase. This is the actual draw command. And what draw erase does is plot the points. We actually set up the points earlier. These are the points. We set up these points to be the vertexes that get sent to the vertex shader. -1, 1 is here. 1, 1 is here. -1, -1 is here. So this is the first triangle. The first 3 points, we're using the triangle mesh, which means then the next point after this is 1, -1, which is here. We're using the triangle mesh method, which will automatically infer the second triangle to be that. So we have the two triangles that fill out this rectangle, which is basically the whole screen. And that's how I am supposed to sort of specify this region. And then each of these vertex points go to the vertex shader. The vertex shader just pass them right through. It doesn't do anything to it. Just pass these points right through, and that defines the region. And then the fragment shader starts going through every pixel and painting them.
Do you have to do any sort of translation between your coordinate with the coordinate that the vertex shader used?
Oh, in this one, I didn't do it. It was implicitly done because OpenGL always chooses that, standard, like this standard, like.
Oh, so it's the same as your coordinate.
Yeah, so I don't have to care about what the canvas size is, whereas in our coding, our Mandelbrot set exercise, we explicitly converted that. Whereas with OpenGL, it does that for you.
Okay, gotcha.
But I probably still have to think about it if I'm going to build UI around that stuff, right? Because I have to convert the mouse coordinates, etc.
Yeah.
But yeah, I just want to give you like a introduction to it.
Yeah, I think the graphic stuff is really fun. It's like math.
Yeah, there's a while back. I'll share this as well. I was learning OpenGL at one point using some of these resources. So this is a curated list of resources that you can use. And this is some of my code that I ended up making. There's a lot of good resources. There are some new ones that I found the other day that I might add to this list. But yeah, just a final word about this stuff. The mental model of how you program this stuff is very different, and there's a different language to learn. So there's also good learning resources for WebGL, but then again, like the WebGL resources, they kind of assume you have done OpenGL before, so they won't go to the the basic concepts as much probably. And one thing about WebGL is they use OpenGL ES instead of the normal OpenGL. And OpenGL ES means embedded systems. And the embedded system means your mobile phones. So most of our mobile phones that we use have a GPU inside of it. And that's that's what allows the scrolling to be smooth, among other things. So basically, WebGL wants to sort of normalize itself so that it can work for mobile phones. So it's not the bleeding edge, because the desktop version of OpenGL is more bleeding edge and has more advanced feature, etc. But WebGL uses a sort of a smaller version, which works on the mobile devices.
In my C++, we had the exercise of like translating a picture, like a PNG, and add like watermark and change like the color scheme. That kind of.
Really?
Well, it's not this, but it's it's simpler. It's just translating like pixel by pixel, but it's interesting. I think it's fun.
Yeah. You can do that using a shader, actually. So yeah, what you could do, it might be an exercise later down the road where you will need to put your image in as a texture, actually. Like that's how you work with image fragments. You make the image a texture, send it to OpenGL, and then you say, hey, you do the Vertex Shader to just draw a rectangle like I did. And then in your Fragment Shader, that's when you do the translation. You read in the pixel from your texture, and then you do any calculation needed to change the color in the Fragment Shader. And then if you do that, it'll be much faster because it's doing it using the GPU processors.
All right, maybe that's something that it will be a cool thing to learn for me, because I did the normal way. If I can do it this way.
The same thing in two different ways. Yeah, it's definitely a good way to learn things.